Okay, so before I get started, I just wanted to make sure that I point out that I'm not a medical professional, and what I will be talking about is based purely in mathematics. It's not based in medicine. If you are looking for resources on the current state of coronavirus or COVID-19 and how that is doing in the world right now, I've listed both some medical references below and some more mathematical references below as well, including a link to Johns Hopkins University's current tracker of the status of the number of cases throughout the world. So that is there. The content of this video is going to be more mathematical than medical. However, the model that I'm going to present and the framework that I'm going to surround this model with is going to motivate why it's important to quarantine, or why quarantines are important in situations like epidemics and pandemics. And you can even apply it to other scenarios that aren't necessarily related to the current state of world health. So as the title of this video suggests, there is a deck of cards involved. Actually, there are two decks of cards involved, but you could definitely follow along with a deck of your own cards if you wanted to, because when I was starting to formulate this video, I actually just used one set of cards, and I ended up finding that I would be better able to present this model if I were to have two deck of cards, because I can use a larger population value than if I just had one. So in the event that you only have one deck of cards, I would recommend using around 25 cards to do this, and you have to sort of adjust some things along the way. But anyway, so the three states that we're going to focus on correspond to three states that you could be in when you have an infectious disease. First, when the cards are just face down, that will represent a susceptible person. Next, if a card is face up and the color of the suit is red, so hearts or diamonds, then we'll say that that person is infected and contagious. And then the third state will be if it is face up and a black suit, so spades or clubs, then we'll say that that person was infected but is no longer contagious. So in this video, we will just be focusing on contagiousness. We won't be focusing necessarily on a death rate calculation or a notion of what it means to become susceptible again to the disease, because this video is more concerned with the effect of quarantine on the spread of a virus. And so for us, contagiousness is actually going to be a better thing to monitor. The next thing we should go over are the transitions. How does a susceptible person become infected, and how does an infected person become not contagious anymore? So for most diseases, in order to become infected, it's probably obvious that you have to be exposed to that disease. And for something like COVID-19 that we're currently dealing with, where people can be infected by other people, the metric, or rather the event that we're going to monitor in order to determine if someone that is susceptible will become infected and contagious as well, is if they were exposed to someone who was contagious. And we'll do that with the cards by checking to see if a susceptible person is next to a contagious infected person. For simplicity, throughout this video, we'll be expecting the probability that an infection occurs to be 1. And that is definitely not always the case, because you could be exposed to a disease and just be lucky and not actually catch it. Medical professionals take precautions all the time to avoid catching diseases that they are exposed to. The next thing that we need to figure out is how we're going to monitor events of contagious people becoming no longer contagious. And so in order to do that, we're going to use the joy of math and simplify it down to one time step being the amount of time it takes for a contagious person to become no longer contagious. And for the purposes of our model, we'll see how that works here in a second with a small example. But first, just to set the end state before we move to the small example, it's important to note that at some point we might experience a state where everyone has been infected and is either contagious or not contagious anymore. Or we could enter a state where there are no more contagious people left. And so those two states, either the disease no longer being contagious in any of the hosts, or everyone having some form of the disease, whether they are still contagious or not contagious anymore, will act as our end state for our dynamical system of people being exposed and infected with this disease. And just to note again, the model that we'll be using here is more of a expression of a principle of and not necessarily what's going on in the real world right now. So at this point, we know how people are going to interact with each other in the form of these cards, and we know what the possible end states of our system are. Let's go through a small example of what would happen in one of these settings. So if you had a cross of cards out on the board and you had one red suit face up card in the middle, then by adjacency, all of the surrounding cards would become infected and contagious. But then, and this is what I meant by one time step earlier, the red card in the center will become no longer contagious. And we'll assume that it took the full period of being contagious to infect the 4 others. So we can say that that middle card is no longer contagious. Of course, this isn't how actual diseases work, but for the purposes of illustration, this will be a good demo to sort of get your head around what effect quarantine can have on a system. So now that we sort of know how these cards are going to interact with each other, we can go ahead and move forward with analyzing a few different models. We'll do 2 of them. And these are spatial epidemic models. So each card will represent a person, and cards that are adjacent to each other will represent contact between people. So again, just to recap, we're going to be assuming that susceptible people can only be affected by contagious infected people, and contagious infected people become non-contagious after they attempt to spread their disease once. So for each of these models, we'll have a population of 49 people or cards, and they'll be arranged in a 7x7 square. So if you have a deck of cards handy and you want to follow along with just one deck, then the largest array that you'll be able to do while following my convention is 4x4. When I was figuring out if I wanted to actually do a video on this, I was using one deck of cards and a 6x6 grid, but I was using on slightly different conventions where I had to do some bookkeeping at each step. So it is possible to do larger sets if you just have one deck of cards. But if not, and you want to just follow the convention that I'm using, 4x4 is the way to go. So the first model that we'll investigate is called, or I guess I'll call it, the random life model. And so in this model, we don't assume anything about the infected persons. We also don't assume anything about non-infected people. So basically what happens is that after every time step, all of the cards get shuffled and laid back out in the 7x7 array. In this model, and with the next model I'll talk about, I would encourage you to think about it as how you're currently interacting with your community. So for instance, you don't necessarily know everyone that you're going to come into contact with every day. And so in this random life model, it would just be that you have no idea of what you're going to do on a given day, and neither does anyone else in the community, and no one has a given routine. So to go ahead and start off the random life model, what we're going to go ahead and do is we're going to lay out our red cards face down. After they're in the 7x7 grid or the 4x4 grid, if you're following along, we're going to go ahead and flip up one of the cards and say that that is our patient 0 or our index case. So once you select your patient 0, go ahead and gather up all the cards and make sure that you don't flip any of them over. Just make sure that they're in the same orientation that they were on the board, and then go ahead and shuffle them and deal them back out. You should have your patient 0, but he should be in a randomized location. To make this easier to start, you can also just pick one card to be patient 0, flip that up and shuffle, with that being the odd card out, and then deal them out. Or you can just, after you select your patient 0, proceed with the first infection. I decided to shuffle here just because I had laid them out before selecting my patient 0 when I was doing the chalkboard recording. For the bookkeeping for this, I'm going to keep track of the number of time steps it's been, which will be n. I'll keep track of the number of total infected people, and then I'll also keep track of the number of contagious infected people as well. So at one time step, we go ahead and infect those around patient 0, getting 4 new contagious patients. And then we say that patient 0 is no longer contagious. Since we're in the random life model, everyone has no routine, so we can gather up all the cards and shuffle them again, making sure that all the orientations stay the same, and we deal them out to get to the start state of time step 2. To finish time step 2, we repeat that process, and we'll see that we jump from 5 infected to 16 infected, with 11 of those cases being contagious. We can repeat this for 3, and we get 35 and 19 infected and contagious cases respectively. Things start to look a little bit bleak as a majority of the cards have already been infected or are infected and contagious. After day 4, there are only 3 non-infected humans left, and then on day 5, everyone gets infected. So it's important to note that doing this model over and over and over again, it's possible that you have someone that never gets infected and just remains susceptible the entire way through. But the important thing about this model is to pay attention to how fast the disease spread through the population. It only took us 5 time steps, or if you want to say 5 days, in order to infect all 49 of the people within our small community. So that was the random life model. It isn't super representative of how everyday life goes, because most of us have routines and things that we plan on doing every day, and certain people that we interact with every day or plan to interact with every day. But if you think about these 49 people being 49 small communities, you can think of it as like different people from different communities coming into contact with one another, and that infection spreading into that other community. The reason I use that analogy is because even though we tend to interact with a lot of the same people day to day, especially for those of us that have regular jobs and go to school and do other things, every day to day we might interact with people that we might not necessarily interact with on a regular basis, whether that be passing someone in the grocery store or even just ordering a drink at a coffee shop. All of these things lead us to interact with people that we generally don't interact with on a regular basis, depending on your habits. But I think I got the point across. Anyway, we should move on to a quarantine model. So how we're going to work with quarantines in this setup is that instead of shuffling everything, what we're going to do is we're going to only shuffle the susceptible and the non-contagious patients. So in order to institute a quarantine in this model, what we're going to go ahead and do is that whenever a person gets infected, before we move around the other people in the model, we are going to move that first infected person to a designated area in the community of 49 people. So in this case, we're going to move the infected people as much into the top left corner as we possibly can. The reason that this implements a model for a quarantine is because in a quarantine scenario, you're limiting your contact with other people and your interactions with them, and sometimes you're cutting them off entirely. It's not the case that everyone who does quarantine themselves can prevent themselves from interacting with other people. People have families and have children and have parents. And so by pushing the contagious patients into the corner, we can get an idea of what it's like for a group of contagious folks to still have the possibility of infecting others, but limit that ability incredibly so. And so when we go ahead and perform this model, we'll see that we actually don't have to deal all of the cards every time. So just to step through this, on the first day, we pick our patient 0, and that patient 0 is then moved into quarantine, and the rest of the cards are, or would be, shuffled if there were other patients. But since everyone is just susceptible and there's one contagious patient, it doesn't change the model to just leave everything where it is and infect the 2 that are adjacent to the contagious patient. So once we have the 2 new infected folks, we're going to go ahead and switch patient 0 to be not contagious anymore, and then move them out of the quarantine zone, since under the assumptions of this model, if they're not contagious, they don't need to be quarantined. Then we'll move the 2 contagious patients into the top left corner. In this case, I use the top row, but you can use the left column as well, because in both cases, it will have a similar effect since we're working with a square number of cards or people. At this point, I'm going to go ahead and iterate this quarantine model on this community of 49 people. The first thing that I want you to notice as we go ahead and step through this model is that the number of contagious infected people at each time step is relatively small. At no point during this run of this particular model are we getting more than 3 contagious people, which is great for this community of 49 people. But I should stress that not all runs of this model will result in a very small number of infected people that are contagious at every time step. In fact, it is possible that everyone at the end of this model is infected with the disease, but it is much, much less likely than in the previous case. And the rate at which this disease is spreading throughout this population of 49 people when they are quarantining themselves should make that a little bit more intuitive. Now that we've gone through both of these models once, it would probably be a good idea to compare them. Now, of course, if we were being statistically rigorous, we would have gone ahead and done a simulation of this process over some 49 cards a couple thousand times and tried to see what the averages were and whatnot. However, the point of this is to give a little bit of intuition behind why quarantines work, and so it isn't totally necessary to go through that statistical argument. At least I don't think so. If you want to spend the time to go ahead and code this and make this into an automated process where you can gather a ton of data points by running through this process repeatedly, that would be super cool, and I would really like to see it. Because I don't have enough time in my life to go ahead and sit down and code that right now, which is unfortunate because that was one of the things I wanted to do. But I thought the accessibility of being able to do this with a deck of cards was really cool. So when we go ahead and plot the total infected people and the number of contagious folks for each of the models, we end up getting some really interesting data. And so if we look at the random life model, we get what looks like a logistic curve for the total number of infected cases, and we get a normal distribution-esque style thing for the number of contagious cases. Whereas with the quarantine model, we get something that looks almost linear for the number of total infected people, and we only get something that is quite honestly kind of flat for the number of contagious people. So even though the quarantine case looks linear and looks like it's flat in terms of total infections and contagious people respectively, when you go ahead and scale this up and you increase the size of your community, I would actually expect the total number of infected cases to be logistic and the number of contagious people at each time step to be normal, like in the non-quarantine case, but to a very, very lesser degree. And this phenomenon actually does a really good job of giving a lot of intuition to this graph. Our random life model is a lot like the first case where someone is apathetic to the state of the world in respect to the pandemic going on. And of course, this person being apathetic would also need to be conjoined with a large number of people also being apathetic. And similarly, in the flattened curved case, we would need a large group of people to be aware and engaging in their own personal well-being in order to make sure that that curve stays flatter. And so in that respect, our two models have done a good job of illustrating why it is important to quarantine. So at this point, I hope I've given you an accessible way to sort of think about how quarantines affect the spread of disease, and hopefully that deck of cards thing was an accessible way to do that. However, at this point, I kind of want to shift to a more general idea. So the mathematical model that we use in order to model quarantine's effect on the contagious spread of a disease used what we call a SIR model in mathematics. So SIR is an acronym for susceptible, infected, and recovered. But in our case, we were using susceptible, contagious, and non-contagious. At least mathematically speaking, there isn't a ton of difference behind changing the titles of our groups. However, in a traditional SIR model, there's usually a transition from recovered back to susceptible or back to infected that we didn't dive into in this video with our spatial model. of a SIR process for contagiousness. If we want to be more general about our model, we could say that it is a SIR model in the traditional sense, but instead of acting on just population values for each of the 3 populations of people, instead it's operating on graphs of 3 colors, where each node is a person that is in one of the 3 populations, either susceptible, infected, or recovered, or in our case, susceptible, contagious, or non-contagious. And then as time goes on, that coloring of the graph will change based on if people were infected or not. And in that case, we even have more freedom than we did in our card model, because in our card model, we were forced into certain adjacencies between people. But in a more general graph model, we could have totally isolated populations or people that have varying degrees of connections and interactions with other folks in the community. Anyway, at this point, that's all I have for you today. If you did enjoy this video, you can go ahead and give it a thumbs up, and you can subscribe for more mathematics stuff that I'll put out here on the internet. I kind of just got really inspired to make this video after thinking about some work that I did in undergrad, and also just trying to make the idea of why quarantine is important in an accessible way. And I hope that the DEC model did a good job of doing that. But if you thought so, you can leave a comment down below. I have a lot more stuff in the description box as well, including some other mathematical models that you can do with the deck of cards in the context of the quarantine problem and just infectious disease in general. So that's down there as well if you're interested in that. But at this point, I am going to shut off the camera and go to bed. As always, I am Nathan. This was Chalk, and I will see you next time.